Morning all. Today we are continuing our lecture on classical and quantum mechanics. So, as you mentioned in our earlier discussion, this lecture series is based on the fifth semester BSc Physics syllabus of MD University. And now we are going to discuss, or we are continuing the discussion of Module 1. Okay, so the topic which we are going to cover in this lecture are constraints and classifications of constraints, and what you mean by degree of freedom, and the general discussion on generalized coordinates and configuration space. Okay, so what do you mean by constraints? So constraints are basically the restrictions imposed on the motion of a particle. Suppose if you have n number of particles, we can impose certain restrictions on the position and velocity of the particles of the system. So such restrictions on the kinematical motion of a system of particles are called constraints. So there are different types of constraints in classical mechanics. So I would like to mention some of the examples here. The first example is the motion of a rigid body. That is, the motion of a rigid body is restricted by the condition that the distance between every 2 points in the rigid body remains constant. Okay, suppose if you have we are considering two particles with the one position vector Ri and another position vector Rj. So the distance between these two position vectors, that is Ri minus Rj, should be constant always in a rigid body. So another example is the beads of abacus. That is, the beads of abacus are constrained to move only within the string. So one of the another major classification or another example is the motion of a gas molecule. So that is, gas molecules are constrained to move within the container. That is, there is no permission to move outside the container. So that is one of the example for constraint. So next we are going to discuss the major classifications of constraints. So in this syllabus, you have 4 major classifications for the constraints. The first one is holonomic constraint, and second one is non-holonomic constraint, and third one is scleronomic constraint, and fourth one is rhenomic constraint. The scleronomic constraint is otherwise known as scleronomous constraint, and rhenomic constraint is otherwise known as rhenomous constraint. So let us look what we mean by the holonomic constraint. The constraint which can be represented in a well-written equation form are known as holonomic constraint. So that means the constraint force, that is the force behind the constraint, can be written as the function of position vector and the corresponding time. So this is a well-written form for an equation. That is, f is a function of r1, r2, comma t. That means r1, r2 is position coordinate and t is the time coordinate. So if you can return this type of equation from constraint, such constraints are holonomic constraints. Okay, so as I mentioned earlier, the rigid body dynamics or the constraint involved in the rigid body is a holonomic constraint. Okay, why? That question is, suppose if you are considering the two coordinates in a rigid body, that is Ri and Rj. So the position or the difference between these 2 points, Ri minus Rj, modulus square is equal to Cij square, where Cij is the constant or the distance between the two particles. So this type of constraint associated with rigid body is a holonomic constraint. So next example for holonomic constraint is a constraint associated with a particle moving on the surface of a circle. Okay, suppose a particle is moving on the circumference of the circle. That is, the particle is restricted only on the surface of the circle. Then the motion can be represented with a suitable equation that will be an equation of a circle. Okay, so you can represent that constraint using a equation. Therefore, such a type of equations, such a type of constraints are known as holonomic constraint. Okay, so here you can see R is a position vector and A is the radius of the vector. Then you can write the condition R is equal to A or is R is minus A is equal to 0. So that is one of the example for holonomic constraint. So the exactly opposite thing happens in non-holonomic constraint. Suppose if the condition for constraint cannot be expressed as an equation connecting the coordinates of the particle, then they are known as the non-holonomic constraint. So basically these non-holonomic constraints are expressed in form of inequalities. Okay, so what are the examples for non-holonomic constraints? So the major example is the constraint involved in the motion of a particle placed on the surface of a solid sphere. Suppose there is a particle which is on the solid sphere, surface of a solid sphere. Let it be an ant. So an ant is moving on the solid sphere. So what is the condition which is going to represent the motion of the ant? So that condition is known represented by an inequality which is r square minus a square greater than 0, where a is the radius of the circle. Sorry, radius of the sphere. That means the particle which is moving on the surface of a sphere can exist only on the surface. So that is a concept which is behind this inequality. Okay, another example is constraint on the object rolling on the rough surface without slipping. Okay, so without slipping, an object is rolling. So such types of constraints are also a non-holonomic constraint. So constraint involved in the motion of a gas molecules is also a non-holonomic constraint. So such types of constraint can only be represented using inequalities. There is no equation which is going to represent this constraint force. Okay, so the conclusion is if you can represent the constraint using a well-written equation, then such a type of constraints are holonomic. And if there is no such equation and we are using inequality, then such types of constraints are non-holonomic constraints. So next classification is scleronomic constraints. So what do you mean by scleronomic constraint? A constraint which is independent of time are known as scleronomic constraint. That means there is no time dependence in this case. Okay, suppose a bead sliding on a rigid curved wire fixed in a space. So such types of constraints, that is a bead is fixed on a rigid curve. So it has only the motion in that string and it is independent of time. So such a type of constraints are scleronomic constraints. Okay. So there is another category which is exactly opposite of scleronomous constraint, which is known as renomic constraints. So renomic constraints are the constraint which is exclusively dependent on the time. So time dependent constraints. So a bead sliding on a rigid curve moving in some prescribed fashion is an example for renomic constraint. Okay. So one of the other major example is a simple pendulum whose length is changing with the time. That is, you have using an extensible string, that is L is a function of time. Then the constraint expressed by the equations are time dependent. Hence, it is a renomic constraint. So one point you should note here is that the renomic constraint is a time dependent constraint because there is a chance the renomic constraint can be under the category of the holonomic constraint also. Okay, so next we are going to the next topic, that is the degree of freedom. So degree of freedom has a very important role in the Lagrangian dynamics. Okay, so what do you mean by degree of freedom? So degree of freedom can be explained as the minimum number of coordinates needed to specify the position of a system completely. So the number of coordinates are known as the degree of freedom. For example, if you are discussing a one-dimensional motion, uh, what are the number of coordinates you are needed to explain that motion? So that means for in one dimension, you need only one coordinate. So that means the degree of freedom is 1. Suppose if you are considering with two-dimensional motion, that means the particle is moving in a plane. So at least two coordinates are needed to describe that motion. So in case of two-dimensional motion, the degree of freedom is 2. So similarly, in three-dimensional, you are dealing with x, comma, y, comma, z coordinate. So that means you need minimum number of three coordinates for the definition of the particular motion. So degree of freedom is the minimum number of independent coordinate needed to specify or define the system completely. So the one of the extension of the degree of freedom is generalized coordinate. So let us look what you mean by the generalized coordinate. So generalized coordinates are the minimum number of independent coordinate needed to define a corresponding the motion of a system. Suppose if you are dealing with n number of particles in a three dimension, then you need total of 3 into n quantities to define the position of the particle. Suppose if you have m number of constraints existing in that system, so you need have 3n number of coordinate and m number of constraint. So the minimum number of coordinate can be obtained by subtracting this m number of constraint from this 3n coordinate. So the minimum number of coordinate required is 3n minus m coordinate, so which are independent coordinate. So the here the 3n minus m number of coordinates are known as the degree of freedom. That is the minimum number of coordinates. So next question arises is which are the minimum number of coordinates? So that coordinates are termed as generalized coordinates. Okay. So the number represents degree of freedom. So that coordinate. That is, for example, in two-dimensional motion, you need two coordinates. So which are those two coordinates? So that answer is x comma y. So x comma y are termed as the minimum number of generalized coordinates. So we can conclude that the minimum number of coordinates is degree of freedom, and that minimum number of coordinate. So that coordinates are termed as the generalized coordinates. Okay, so generalized coordinates are calculated by excluding the corresponding constrained forces or constrained equations existing in the system. Okay, for example, if you have a diatomic molecule, so each molecule you have three coordinates. So that is 3 to 6 coordinate is needed. But there is a constraint connection between these two molecules, these two atoms in the atomic molecule. So the constraint is 1 and the total coordinate is 6. So overall you need only 6 minus 1, 5 coordinates. Okay. So the generalized coordinates are usually represented using the letter small q, that is q1, q2, etc. up to qn for n number of particles are using for the representation of generalized coordinate. So one of the major point you should note is the generalized coordinates are always independent coordinates. Okay, so that is one of the very important discussion regarding the generalized points. These are a few examples to evaluate the degree of freedom and the generalized points. So one of the classic example is simple pendulum. So if you are considering a simple pendulum, the length of the pendulum capital L is always a constant. So the motion can be represented using a single parameter, that is theta. So you need only theta to define the complete motion of a simple pendulum. So the degree of freedom is 1. That is only you need only one coordinate. So what is that one coordinate? That one coordinate is theta. So theta is the generalized coordinate, and that number of coordinate is 1. So that is the degree of freedom. That is the concept behind the degree of freedom and the generalized coordinate. Okay. So another example is the double pendulum. That is the two pendulum which are oscillating together. That is one pendulum is connected end to end in another pendulum. So that is known as double pendulum. So what is the degree of freedom of a double pendulum? So that means for the first pendulum you need only one coordinate, that is theta 1, and for second pendulum you also need another coordinate theta 2. and L1 and L2 are remains constant. So that means in order to define the oscillation of a double pendulum, you need two independent coordinates. So degree of freedom of a double pendulum is 2. So which are that coordinates? That coordinates are theta 1 and theta 2. So theta 1 and theta 2 are the generalized coordinate for this system. Okay. So today we are concluding the lecture with the last topic, configuration space. So what do you mean by a configuration space? So as I mentioned earlier, if you have k number, small k number of constraints, the total degree of freedom n is equal to 3 into n minus k, where n is the corresponding number of particles in the system. Suppose if I n number of particles, you need total 3 into n number of coordinates. If there is k number of constraints, then the degree of freedom is n is equal to 3n minus k. So you can consider or you can assume a space with a dimension of small n. So n-dimensional space, which is formed using the generalized coordinates q1, q2, etc. to qn, is known as configuration space. Okay, so the configuration space is a n-dimensional space formed using generalized coordinate. So that n dimension is determined by the number of generalized coordinates. Okay, or otherwise the degree of freedom of the system. So that is known as configuration space. So most of the problems associated with the Lagrangian or Hamiltonian dynamics is solved in the configuration space. Okay, so the configuration space is something which is related with the generalized coordinate and corresponding degree of freedom. Okay, so we are concluding the lecture 2 with this point. Okay, so we are in a way to enter deeply into Lagrangian and Hamiltonian mechanics. So next lecture onwards, we will seriously look into the corresponding terminologies related with the Lagrangian mechanics. Okay, thank you.